Here, this is the mock paper from 2017, the U-values question. It's usually question 5 in the paper. So we're told that an existing house is a cavity wall with a 200mm full fill cavity. So it's a cavity wall, 200mm full fill cavity, and that the wall has the following specifications. You're told the thickness of the different parts of it, and you're told thermal data of the outer leaf, inner leaf, and of the cavity. So the first part is you're asked to calculate the U value of the above wall. So to begin, if you're not 100% sure what the sketch looks like, or what the actual detail looks like, draw a quick sketch. So you have your external render, you have your external block, you have a 200mm cavity filled with insulation, you have a 100mm inner leaf, and you have 16mm of a internal plaster. So it's no harm just to draw that. That's 20mm external render. Then you have 100mm outer block. You have 200mm expanded polystyrene filling up your cavity. You have 100mm internal leaf, and you have 16mm internal plaster. So that's what your sketch looks like. Next, you'll have to make out a table. So you have your different components, and write those there. And then you're told the thickness of materials, which you have to convert to meters. You're told you have the conductivity of a number of materials, so we'll need to have a chart there for that. And you're told the resistivity also of one of the materials, so you have to have resistivity in there as well. And we have to calculate the resistance. And I would always leave space on the right hand side here for calculations. So these are your components. Then you have the thickness, and the unit I use, or sorry, the symbol I use for thickness is L, and the units will be meters. Then you have your conductivity, and the units, or symbol for conductivity is K. Units are meters, degrees, centigrade per watt. Then you have resistivity. I just usually write down small r for resistivity, and the symbol for resistivity is small r, and the units for it are meters, degrees centigrade per watt. As you can see, I wrote that one down wrong. That should be watts per meters, degrees centigrade. And over here you have your resistance. Symbol for resistance is capital R, and the units are meter squared, degrees centigrade per watt. Always a good idea, I think, at the very start of the question also is to write out your formula that you're going to use. So U is equal to 1 over RT, and then the other one that you're going to use is R is equal to L divided by K, or the other one is L multiplied by small r. And this here is where you're writing your calculations. Okay, so your different components. Now there are different ways you can write this out. If you look at your thermal data, you're given the resistance of the external surface, external plaster, conductivity of the concrete block, expanded polystyrene, conductivity of the internal plaster, and the resistance of the internal surface. So we have an external and internal surface resistance. So I'm going to start with the external surface. So the external surface, we're given the resistance of the external surface as 0.0 0.048. So we can actually write that into the resistance column. The next one in then will be my external render. And the thickness of the external render is 20 millimeters, so I have to convert that to meters, so it becomes 0.02. Conductivity of the external render I'm not given, I'm given the resistivity. So the resistivity is 2.170. So I put that in here, 2.170. And I'm asked to calculate the resistance of it. So the formula I'll use, because I have the thickness and the resistivity, will be this one here. So it's 0.02 multiplied by 2.170. I'm going to add that up together. That'll give me 0.043. 434, but 3 decimal places is fine. Then you have the external block. So the external block or external leaf, the thickness of it is 100 millimeters. So when I convert that to meters, that gives me 0.100 or 0.1. I'm told the conductivity of the concrete block is 1.320. So I'll put that in here in this column, 1.320. And then I need to work that out. So the formula I'm going to use for this one is L divided by K, thickness divided by conductivity. So I'll put my calculation out here. So it's 0.1 divided by 1.320. And that gives me 0.0758, so 0.76. Next one in is my cavity, but my cavity is filled with insulation. If you look at your data here, you'll see that you're not given the resistance of the cavity this time. That's because it's filled with insulation. So I'm told that the insulation is 200 millimeters wide. So that becomes 0.2. I'm told that the conductivity of the insulation is 0.037. That goes in here, 0.037. So I write out my calculation again, 0.2 divided by 0.037, and that gives me 5.405 to 3 decimal places. So we have the internal block done. All we have to do now is the internal render or internal plaster. Thickness of that is 16. So when I convert that to meters, it becomes 0.016. Conductivity of that we were given as 0.220. Calculation for it then becomes 0.016 divided by 0.220, and then when I calculate that out to 3 decimal places, it gives me 0.073. And then final part is our internal surface resistance, which is given here. So don't forget that one. So internal surface, and we're given that, so we don't need that, likewise up here. So we're given that as 0.122. Okay, so we have to then add those together, and that gives us our RT, which we were looking for up here. So we add those up together, and remember now you're looking at 3 decimal places. So when I add those up together, it gives us 5.843, or around that figure. Okay, it might be 4 when you add them up, depending on how you worked out in your decimal places. And just write in your unit, that's meters squared degrees centigrade per watt. So the next thing is we want to find our U value. So U value equals 1 over RT, and write this out again. It's equal to 1 divided by 5.843, and that is equal to 0.171, and I had a 1 after as well, 3 decimal places, up to you. It equals watts per meters squared degrees centigrade. That is your answer for part A. So for part B of this question, it is proposed to build an extension onto the house in order to maximise floor space. It has been suggested that a 100mm lightweight concrete block be used on the inner leaf. It has also been suggested to change the insulation from expanded polystyrene to phenolic foam board. By doing this, thickness of the wall can be reduced but maintain the same U value as the existing wall. Given the following data, calculate the wall thickness which may be achieved while maintaining the same U value as above. They give us the conductivity of the lightweight concrete block. They give us the conductivity of the phenolic foam. So the first thing to note is, just carrying on from part A again, the U value that we had, that's the existing, I suppose, U value, is equal to 0.1711 watts per meter squared degrees centigrade, and that existing resistance was 5.843 meters squared degrees centigrade per watt. So we'll use that later. Right, so just to give you an idea of the structure again. So the first thing we're going to do is we're going to calculate the resistance of the wall when there's no insulation in it at all. So we're going to have our external render, which was 20 millimeters. We're going to have our external leaf, which was 100. We'll have our cavity there. We don't know what thickness of cavity we have yet. We'll have our internal leaf, which is 100 millimeters lightweight concrete now, block, and 16 millimeters. Okay. Okay, so we'll start with our chart again. And you'll have your components there. You'll have your thickness, you'll have your conductivity, and you'll have your resistance, and you have your calculations there. So you'll have your components, parts, whatever you want to call it. You'll have your thickness, you'll have your conductivity, and you'll have your resistance. So we'll start with your external surface. Don't forget you have your external surface and you have your internal surface. You have your external render. You have your external leaf, external block. You have your inner leaf or internal leaf, because we're leaving out the cavity here now this time. You'll have your internal render, and you'll have your internal surface. So the thickness of the surface doesn't count, no conductivity, and you're given the external resistance 0.048. External render, as before, you just write these numbers out again. 0.020. You're given the external leaf, internal leaf. Okay, and all these were filled out before. You have your external conductivity. Now this one is different, the one for the inner leaf. Remember we changed to the lightweight concrete block, and we were given the conductivity for the lightweight concrete block as 0.12. So we're going to put that in here, so it's 0.12. And then you're given the conductivity for the internal render, and then your internal surface, you're given the resistance of that, and the internal surface was 0.1220. And all that information was got from this chart above here previously. Okay, so external render we got before, so that's 0.043. Just check that. Yep, and then you had your external block, and that was 0.076. Now the internal leaf, we have to use our formula again. R is equal to L divided by K. So if we put out a calculation here, it's 0.100 divided by 0.12, and that gives us 0.833. And then this one here, we got it from before, 0.073, and then we have to add all those up to give us our RT. So when we add those up, all up together, it will give us 1.195. That's our total resistance. So you add those up. So that is the resistance of the wall with the lightweight concrete block and without insulation, and using, as I said, 100mm lightweight concrete block. Okay, that gives a resistance of 1.195 square degrees centigrade per watt. Okay, so we want to find the thickness of insulation needed. And don't forget, we're using phenolic foam. And we're told that conductivity of it is equal to 0.018 watts per meters degrees centigrade. So we need to find the resistance of the phenolic foam, first of all. And that'll be equal to our existing resistance, which was 5.843, minus the resistance, or the new resistance, which is got by having our lightweight concrete block, and that's the resistance of the wall without the insulation. So if we have the resistance of the wall up here, which gave us our U value, and that's what we want to get again, we need to subtract the resistance of the wall that we got without the insulation. So that will be equal to 5.843 minus 1.195, and that equals 4.648, and that's meters squared degrees centigrade per watts. So that's the resistance of our phenolic foam. We'll go back to our formula. R is equal to L divided by K. Therefore, L would be equal to R multiplied by K. So if you keep L on one side and you bring K up here, so that equals 4.648 multiplied by the conductivity of our phenolic foam, 0.018, and that will give us 4.648 multiplied by 0.018 equals 0.084. It'll be equal to 84 millimeters. And if you remember back here, what we were actually asked for was to calculate the wall thickness which may be achieved while maintaining the same U value. So that's the thickness of our insulation. So the new wall thickness will be equal to 20 plus 100 plus 84 plus 100 plus 16, and when you add those up, that will give you 340 So this is part C. You're asked to use notes and sketches to show the correct detail between a concrete floor and external wall to minimise thermal bridging. So basically we'll be using insulation and thermal blocks. So in the diagram here you can see on the foundation, on the inside leaf, you've got autoclave concrete blocks. Now these are really your thermal blocks. You can just call them thermal blocks. So with thermal bridging, basically a lot of the heat is lost from the room between the floor and your wall down through your foundation. So what we need to put in is our thermal blocks between the floor and our wall, and also we need to add in insulation around the perimeter of the edge of the wall and the floor. So you can see that there in your diagram, and the combination of these two measures will reduce the thermal transmittance or thermal bridging between the wall and the foundation and the floor.